This lesson has two parts. The first part I'm doing real life chemistry, and you don't need to write anything during that time, just listen and try to understand. And then the second part I'll do the worksheet, and then you should be writing because you have your worksheet to fill out. So here's a roll of magnesium metal ribbon, and you can see it weighs 24.2 grams, which is equivalent to the molecular weight of magnesium. So this is 1 molecular weight worth of magnesium. So this is a big long thing to say when you just want to say I got the same mass as the periodic table. So chemists have a shortened word for all of this. 1 molecular weight worth is called 1 mole. And you can see it's just the first part of this big long sentence. 1 molecular weight worth 1 mole. So this is a word that you'll need to recognize and use intelligently. That's the lesson of the day. So now I'm going to use some salt. Salt is NaCl, sodium chloride. And I'll try to get 1 mole of salt. That's 1 molecular weight worth. So here's sodium on the periodic table. It says 22.99. I'll say that's 23. Here's the chlorine on the periodic table. I'll say that's 35. So here's 1 molecular weight for sodium chloride. It's 58 grams. So if I get 58 grams of salt, I'll have 1 mole of NaCl. So there we go. That says 58 grams of NaCl. That's 1 mole, 1 molecular weight worth of sodium chloride. So we've changed the name, but we haven't changed the concept. Previously you knew that in 1 molecular weight worth you get 6,000 atoms or 6,000 molecules. And now that's still true, but we're just calling it a much shorter name. 1 mole has 6,000 atoms, so this 1 mole of magnesium, 6,000 atoms. And this 1 mole of sodium chloride has 6,000 molecules. So if you get a mole, you get the same number of particles. That's crucial to understanding the value of the mole. Moles have great value in chemical reactions. You can react magnesium with HCl. I'll do it in real life in just a little bit. And it should make sense to you based on the periodic table that this is 24 grams. That's how much magnesium weighs. HCl weighs 36, so 2 of them weigh 72 grams, etc., etc. However, if you grasp the idea of the mole, you can see that this can be simplified greatly. Since 24 grams is 1 molecular weight worth, it's 1 mole. 72 grams is 2 molecular weights worth, it's 2 moles. 94 grams is the molecular weight of MgCl2, it's 1 mole. 2 grams is 1 mole of hydrogen gas. This has value because I'm not going to weigh the HCl. I'm not going to weigh 72 grams of this liquid. I just need to get the right number of molecules. I need to get the right number of moles. And that's what this label is all about. You've seen this molar many times. It is a concentration of moles per liter. These labels refer to how many moles, how many molecular weight worths of HCl is in each liter of the solution. So here I've made the little cartoons. 6 molar is more concentrated, so I made it more orange. 6 moles in each liter if it's 6 molar. 2 moles in each liter if it's 2 molar. So I didn't have an official 1 liter bottle from school, but this is really close to 1 liter. So imagine if I put into this bottle 2 molecular weights worth, that would be 72 grams of HCl, then this would be 2 moles in a liter, and it would be 2 molar. To make 6 molar, I'd have to put 6 molecular weights worth. That's 6 times 36, or 216 grams of HCl in the 1 liter bottle to make it 6 molar HCl. So now, this is a mole of magnesium. It will react with 2 moles of HCl, which means that this volume I have is not enough. I need a full liter of 2 molar HCl to react with this much magnesium. Since I don't have a liter of 2 molar HCl, I can't react all this magnesium, but the idea of the recipe is that it's ratios. I could do 1/10 of a mole, and then I'd need 2/10 of a mole of HCl. What I'll actually do is 1/10 of that. So 0.01 mole magnesium requires 0.02 moles of HCl. It's just a 1:2 ratio. No matter what numbers I use, it's a 1:2 ratio. This is something that I can do, and I won't run out of HCl. Here I've done some dimensional analysis to calculate, if I did this pink scale reaction, how much magnesium do I need? It's 24 grams for 1 mole. I only need 1/100th of a mole. It's 0.24 grams. For the HCl, I've calculated I need 0.02 moles. 1 liter has 2 moles, so that's 0.01 liters, which is 10 milliliters. That's what I'm going to do in a small beaker or test tube. So here I've got the 0.01 moles, 0.24 grams of magnesium. I put 10 milliliters of the HCl in my cylinder, ready to run the reaction with the proper ratios. 0.02 moles of HCl in the beaker, and in goes the magnesium. I'll tear it up a little bit so it fits better. In goes the magnesium, and you can see a lot of fizzing, some steam arising from the beaker. That's the exciting reaction we know and love. Here I put a makeshift lid on the reaction beaker. I'm not in the lab, I'm in my office. I want to keep the fumes in the beaker as much as possible. So I'll come back in a little while to see what it looks like at the end of the reaction. So it's been about half an hour. Reaction looks complete. There's some little tiny pieces of magnesium left over, so that suggests my measurement of the HCl was probably a little inaccurate, or maybe some evaporated when it was bubbling and steaming so much. That's a possible reason for leftover magnesium. But I'm happy with it. The solution is clear. That's the magnesium chloride that's aqueous. It looks great. Here is the worksheet. So fill this out as I do. You've already seen this example. Sodium and chlorine make sodium chloride. That's salt. We round this number to 23. We round this number here to 35. We add them together to find the molecular weight, which is 58 grams. We're saying that's 1 molecular weight. It's 1 mole. It has the AM 6000 concept. 1 mole is 6,000 molecules. And we can write that concept as a conversion factor. You can see I've got something on the top, something on the bottom. You can flip it over if you need to. Example 1 is supposed to be very easy. I'm filling it out on screen. The given, well, the question is how many grams are in 2 moles of sodium chloride. So I put the given 2 moles in the box, and I need a conversion factor now. Moles goes on the bottom. So if this happens to you like it did, just hit delete until it pops back into place. And since I'm looking for grams, that's what goes on the top. That's what goes on the top. Grams on the top, moles on the bottom. Now I need the actual numbers. I'm using this conversion factor here that's in purple. 1 mole. I'm just hitting delete so that it fits in the box. And that is 58 grams. So this is now a beautiful dimensional analysis setup. Moles will cancel moles. So this here cancels these moles here. I can't actually strike it out, but I'm hoping you understand the concept. These moles in the beginning cancel these moles in the bottom. So now all I have to do is math. I'll write the math here. You don't really have to write it, but it will be 2 times 58 is the math, and that's 116 grams NaCl. That's my final answer. I'll highlight it because I'm doing this on screen, so I can say, boom, final answer, 116 grams NaCl. So there's a simple example. Example 2 will be a little more complicated. And it's not NaCl anymore. It's now HCl. And you saw in my video, 2 molar HCl has a definition of 2 moles in each liter. And in here in the yellow box, I said a liter is 1,000 milliliters. So this will be 2 steps. It's dimensional analysis all the way through. How many moles? So that's where we want to end. 65 milliliters of 2 molar HCl. Start with the given, 65 milliliters. I'm going to write this unit of measurement here. I know it has to go here in the answer, so I'm going to type it here in the last conversion factor. So this is a strategy you can use with dimensional analysis. Whatever answer you want to end up with has to go right here. Everything else is going to cancel out on the way to that answer. All right, dimensional analysis says the bottom here has to be milliliters. Once again, hit delete if it overflows the space. And on the top is a little questionable. So there are different strategies. But in this case, I'm going to say I need to use this concept, this picture concept, 2 moles in each liter. And the only place moles is going to appear in the whole setup is right here at the end. 2 moles in each liter. There. I have made the conversion factor, and that helps me figure out what conversion factor to put here. Milliliters will cancel milliliters. I now need something to cancel these liters. So that means the top here has to be liter. Liter, they'll cancel. And now I just use what's in the yellow box as a conversion factor. 1 liter is 1,000 milliliters. So that now looks great. Liters here, cancels liters here. Milliliters cancels milliliters, only moles survive. I'm now ready to solve the problem. So I'm getting out my trusty calculator. Crash. Trusty calculator. And I'm trying to do the math. So it's 65 times 1, but divide by 1,000. You can see it right there on the bottom. Divided by 1,000 That gets me 0.065 liters, then times 2, divided by 1, I'll skip. My calculator is telling me 0.13 moles of HCl is the final answer. I'll go ahead and highlight that as final answer. So there's example 2. Take a look at the dimensional analysis. See if it makes sense to you. And now I'll do example 3. The problem has a balanced equation. You can see I put the coefficients in blue here. Big 1, big 2. And normally the ones aren't written, but this will make it easier for you to see the ratios. The question asks you to find how many moles of sodium carbonate are needed to react with 0.36 moles of silver nitrate. Here's the silver nitrate, here's the sodium carbonate. And in blue, I wrote the words coefficients provide a mole ratio. So it should make sense to you that 1 molar mass of sodium carbonate reacts with 2 molar masses of silver nitrate. So those are moles. The problem is easy to do here. We don't need any of the weights. You don't need, look at my camera picture now, you don't need your periodic table if you have a balanced equation. You don't need to find the masses if we're just talking about moles. This is one of the main simplifications or advantages of saying I can use moles. So let's look at the actual problem. The given is right here, 0.36 moles of AgNO3. Remember, you can make this 3 subscript by formatting the text into a subscript. And you can also just use control comma. See, control comma. All right, so there's the 3 down low where it's supposed to be. The answer is supposed to be moles of sodium carbonate, so I can already type that here. Moles, Na2CO3, and I'll do the control comma deal and the control comma deal. All right, so now I need what's called a mole ratio. I want moles of Na2CO3 on the top. I want moles of AgNO3 on the bottom. And once again, let's make it fit in the box. Okay, there we go. Moles of sodium carbonate on the top, moles of silver nitrate on the bottom. If you want to make this look nice, you can. In this case, I'm not going to bother. What's the ratio? 1 sodium carbonate here for every 2 silver nitrates. So I'll type a 1 right here where my cursor is. 1 mole sodium carbonate for 2 moles of silver nitrate. Now it fits in the box. If you want it to be grammatically correct, you can say 1 mole, singular, of sodium carbonate for 2 moles silver nitrate. So that's the setup. It's pretty simple, as you can see. 0.18 moles sodium carbonate is the answer. And I got that by just taking my given 0.36 moles dividing by 2. So that's final answer right there. So I'll highlight it. Nice blue color this time. And this may help you, I'm not sure. But you could say, since the mole ratio came from the coefficients and the coefficients are blue, we might be able to make these blue as well. Yeah, try again. There we go. This time it'll work, I think. Blue. There it is. So now the blue conversion factor corresponds to the blue coefficients. That may help you see how does it work. I'll try to make this 2 correct. This is optional. So let me get rid of the 2. Let me highlight the A. Let me show my equation tools. And now I want to view the equation toolbar, which is here, and I can click here and say, I want a subscript. So I chose that one. Now, I should be able to type in the 2, but I have to use a right arrow. This is so unintuitive to me. I'm typing right arrow, and now you can see there's a little space where I'll put in the 2. And I can do the same thing with this 3, delete the big 3, and then highlight the O. And again, go here to the equation tools, subscript, right arrow, 3. That's how you do it.